Hello, people. You're welcome to Learn Better Computing. And today we'll be talking about recurrence relations and the master's theorem. The master theorem is just one of those methods we use to solve recurrence relation. All right. Recurrence relation is involved when your function is recursive. When your function is recursive in nature, then you express it mathematically using a recurrence relation. As the name implies, recurrence, that means it keeps recurring, right? For instance, if I have a function like this, let me go to my marker board. If I have a function like this, t of n is equals to t n minus 1 plus 1, right? This is a recurrence relation. Why is it recurrence? Because it records itself, all right? And you want to put it in the form of a piecewise notation and saying that t of n is 1 if n is let's say 1. You see that? Else it is t n minus 1 if n is greater than 1. You see that? So this is a piecewise formula for this expression. And what is this expression doing? It is like reducing the input by 1, then you add the work done to combine all the results together. All right? It's a kind of reduce and conquer approach. It's different from what Master's theorem is used for, which is divide and conquer approach, right? So now if I want to solve this using my code, I'm going to define this as, assume that this is a factorial function, because factorial function is also defined with recurrence relation like this, right? So I'm going to say, you know how factorial function works, right? So if I say 5 factorial is what? It is 5 times 4 factorial, right? Because 5 factorial is 5 times 4 times 3 times 2 times 1. See that? So as a result, I can say 4 factorial is 4 times 3 factorial. See the way you are reducing the work? Then 3 factorial is 3 times 2 factorial. Then 2 factorial is 2 times 1 factorial. And 1 factorial, according to our piecewise definition here, when n is 1, you return 1, right? So that when n is 1, you return 1, right? So that means this place is going to be 1. You see that? So that means I can say that this function here returns 1. So this is going to be 2 times 1, right? 2 times 1 is going to give me 2, right? It's going to give me 2. That means 2 factorial is 2. So I'll pass the 2 to this place. You see that? So that means 3 factorial is 3 times 2. This is 6. So I already solved for 3 factorial. So I'll pass this 6 into this place. You see that? So it's going to be 4 times 3 factorial, which is 6. I already solved it. And that's 24. You see that? So this 24 now is 4 factorial. I'll pass that 24 to this place. So it's going to be 5 times 24. Okay? And that's going to give me 120. See that? So that is the result for 5 factorial. See the way I solved it now? So let me convert it to code and say I'm going to have something like this. Factorial of n. Now if n is equals to 1, then return n or return 1. It's the same thing. Return n. So when you return n, that means you are returning 1, right? Because n equals to 1. Else, return, you call the function again, factorial n minus 1. See that? Times n. So this now is the code you will use to solve this recurrence relation. All right? So this is what recurrence is. Okay, it could be expressed in a piecewise manner like this, and this could be converted to a code, and you can see that it is recursive. A recursive function is a function that calls itself, and that is what is going on here. All right. So with that said, let's move on to our slides. So in the context of algorithms, is a powerful tool for describing the time complexity of recursive functions. It breaks down a complex problem into a simpler one. All right. So by reducing before conquering or dividing before conquering. All right. Then let's see an example of recurrence relation. Because we are looking at it in the context of, Master's theorem, we'll be considering it using the divide and conquer recurrence relations. All right. So you have a typical recurrence like this. Look like T of n equals to A Tn divided by B plus F of n. Tn is the total time to solve a problem of size n. A is the number of recursive calls made in each step. Tn divided by B is the time for each recursive call where the input size is divided by B. F of n is the time to do the work outside of the recursive calls, meaning combining results together, right? Let's see an example. This is it, T of n. T of n is equals to Tn divided by 2 plus big O of 1. So it's used for binary search. We call one recursive call on a sub problem of half the size, and the work done at each step is constant. So the recurrence relation is this. So let's see how we use Master's theorem to solve this. Master's theorem is a shortcut for solving recurrence relations of the form this. So it's not used for solving all recurrence relation, only the recurrence relation that has this form, A Tn divided by B plus F of n. So this A Tn by B is the recursive part, all right? Then this F of n is the work you do by combining the results together. Now, is a key tool for solving and analyzing the runtime of divide and conquer algorithms. All right. Now, the theorem has three main cases, which depend on comparing the function f of n to the critical function n to the power of log a base b. Now, we already know what a is, we already know what b is, right? So if you are given an example like this, we can tell how to solve it, right? So let's go our marker board. We have t of n to be equals to Tn by 2 plus big O of 1, right? In this case, A is 1, B is 2. And f of n is big O of 1, right? So that's a constant right there. And this is like n to the power of 0, because n to the power of 0 is 1, right? So I can say D is 0 in this case, all right? So now, why did I make this a D, right? Because of these Master's theorem formulas. You see this? So these are the three cases. Remember when we are here, we are told that we have three main cases, right? So these are the three main cases. So when D is greater than log A base B, that means D dominates, f of n dominates. So it's going to be n to the power of D, big O of n to the power of D. If they are both the same, then you go by n to the power of D log A base log n, right? Then if D is lesser than log A base B, it's going to be n to the power of log A base B, because log A base B dominates since D is lesser than log A base B, all right? So with that said, we want to solve this guy, right? Now let's go back to our marker board where they have all our ingredients, and this is what you get. So log 1 base 2 is 0, and D is also 0. So D is the same as log A base B. What do you do in that case? You're going to say it's going to be n to the power of D, right? Then log n. So what this will tell you that it's going to be n to the power of 0 log n. N to the power of 0 is 1, right? So everything is going to be big O of log n. You see that? So big O of log n. So that's the binary search time complexity, big O of log n. All right. So that's it with respect to this one. Then, so you want to note this guy is easy to understand and to apply. All right. So these are different examples. This is the algorithm binary search. We did this already, right? So what about binary tree traversal? We have this function, but now A is more than 1, right? Whereas the work done to combine the result together is still a constant time. So how do you solve this? So let's move on to our marker board. And so you have T of n is equals to 2Tn by 2 plus big of 1. So in this case, I know that D is 0, then A is 2, B is 2. So log A base B is 1, then D is 0. So that means D is lesser than log A base B, right? So in that sense, my result is going to be n to the power of log A base B, right? So what will that be? That will be n to the power of 1. That will be big O of n, right? So that's the idea. So that's why you have this runtime to be big O of n. See that? Big O of n. Then for optimal sorted matrix search, it goes like this. Now, we may not be able to apply the master theorem because f of n does not really have a term where we can take to the power of, or we can take n to the power of. What you have here is log n, right? It is not like a constant. It's not like n, right? So that's why I want to apply Accra-Bazzi theorem, right? So this is beyond, master's theorem cases. Then what about the mesh sort? The mesh sort says that T of n is equals to 2T n by 2 plus big O of n. And the runtime is n log n. Why isn't n log n? It's based on the application of the master's theorem. This one, okay? So this guy, right? So let's see how it works. Let's go back to our marker board. We are told that mesh sort is this. Mesh sort is this. We said T of n. Tn is equals to 2Tn by 2, right? Plus big O of n. So now I already know that my D is the power of n, which is 1. A is 2. B is 2. So log A base B is 1, right? So now I can tell that D is equals to log A base B. So as a result, I can say that this is n to the power of D log n. And this is like n log n, right? Because D is 1, right? So this is 1, invisible 1 here. So that's big O of n log n, all right? So that's it. So that's it with respect to this third one. So you can see it's n log n, all right? So these are the cases. You want to look at this. So the case of this is when f of n is equals to this, right? Okay, so the recurrence relation has a solution T this, right? That means the time complexity is determined by the work at the final recursive calls, right? The leaves of the recursive tree, right? Then case 2, the work is evenly distributed. That means it's equivalent, right? So D is equals to log A base B. And that's when you involve the logarithm, all right? Then for case 3 is when you have this work done at the root dominate, right? So that means f of n is lower bounded by this. So f of n dominates. So this is going to be n to the power of D, all right? So that's the idea. Okay, so this one, you are taking the D as the most significant. So it's going to be n to the power of D, right? In this case, that is the same with this case. The same with this case, all right? The same with this case. Then when they are the same, it's the same with this. When it is the first case you are looking at, right? So you can see that this guy dominates, right? So it's going to be n to the power of log A base B. And that is what you have here, All right. Okay. So we have looked at 3 cases. So these are examples. So if you follow the same examples, you can see that we are adding epsilon because it is not, according to the proof, it is not exactly log a to the power of b. It is minus epsilon. Epsilon is the smallest value you can get to 0. Smallest positive value. So it's not really so significant, but just for the sake of accuracy, you may want to add it. All right. So that's the idea here. So log a base b, which is a is 3, b is 2, right? Log a base b is 1.5. Whereas f of n here is a linear function. So d, the power of n, is 1. Compare 1 to this guy. See that this guy dominates. So your result is going to be n to the power of log a base b. And this is what you get. All right. There's another example here, which is like the one we already solved, which is we already solved this, which is merge sort. And that is where we have n log n. All right. So we did that already. There's another example here where you have a to be 3, b to be 4, then d to be 1. All right. So in this case, d will dominate because log 3 base 4 will be lesser than 1. All right. Log 3 base 4 is 0.792. So d will dominate, right? So that means it is lower bounded. So n is lower bounded by this. So that means n will dominate, right? So it's going to be big O of n to the power of d, and d is 1. So it's also, if you use theta, you use big O, you're also good, right? So theta. That's it with respect to this recurrence relations and Master's theorem. All right.